Okay, Assalamualaikum warahmatullahi wabarakatuh. Right, so before we move into AC drive, right? So we know that AC drive will involve induction machine, synchronous machines. Okay, so these machines are actually a three-phase, involved three-phase system. So I would like to go back and do some revision on the three-phase system, and then we look back on the circuit operation of the induction machine. We look into the fundamentals of how the induction machine rotates. Okay, so we're going to look into what is the fundamentals, the theory behind the rotation of the induction machines. And then we look into the circuit parameters, and then the equivalent circuit, because this is going to be used for the AC drive control. Okay, AC control, AC drive. Right. So we come back to, or we go back to the three-phase connection, three-phase supply. Okay, we do have two type of connection, which is Y or delta connection, isn't it? Okay, there's always either Y connected or delta connected system. And for Y connections, we have the VAN or VBN and VCN, and the negative terminal of each phase voltage here will be neutralized. Okay, there will be a common point, right, and whereby all these negative terminal will be common on this point, and the terminal for voltage AN, BN, and CN will be connected to the load of your induction machines. That's what we're going to do next, right? So let's look at some basic. We start with, of course, this is we write the equation based on the what form is this? This is known as a polar form, isn't it? And this is a polar form. We can also represent the voltage in terms of rectangular form. Polar form, you have the degree, and the rectangular will be in the form of cos theta plus j sine theta, isn't it? Yeah, right. So we start with the VAN. So in phasor diagram, we're going to draw such that we have this as a VAN, and then the 120 degree, and another one will be the VCN. Okay, so this will be VBN and VCN, and between all this phase voltage there will be 120 degree. So VAN lead VBN by 130 degree, and then we have another VBN lead VCN by 130 degree, and of course VCN with what do you call it, uh, further minus 130 degree lagging, lagging. So VBN lag VAN by 130 degree, and VCN will be lag VAN by minus 240 degree. So that is a phasor diagram, and by uh, when we want to VAN, we refer to that point, to the neutral point. So that gives you the phase voltage. Isn't VAN, VA, VN. VA minus VN, so we have VAN, so that also equals to the phase voltage. And now how we can get the voltage between V and B? So this is known as line. So we have line to line voltage. Okay. So VAB. So how to get that? So we use the VA vector, which is VAN minus VBN, and therefore we give you a VAB, isn't it? Yeah? That means if you want to draw it on the phasor diagram, So you're going to draw VAN first. So that is exactly what's a VAN. And then minus negative VBN, which means this is VBN. So you need to get it negative or the opposite direction of that. And therefore that will be at the tips of your VAN. Here you continue to have minus VBN. So you're going to do that, isn't it? And so you're going to have that as a minus VBN. And therefore the voltage VAB will be that one, isn't it? So that will be the line to line voltage, which is VAB. Okay? And we know that VAB will lead, L-E-A-D, lead the VAN by 30 degrees. How to prove this? How to prove that the line to line voltage here is 30-degree leading the VAN? And that can be achieved by using the rectangular form, right? So you need to convert that into rectangular. So that will be VAN minus VBN. So therefore that gives you V phase with the angle of 0 degree minus V phase with the angle of minus 120 degree. Right? So that gives you VAB. Okay, so you need to convert that into rectangular form. To solve this, you need to convert that into rectangular form. And therefore, the next page, you look at the next page, that gives you the rectangular form here. So that is V phase, and then the angle should be converted into rectangular, which means we have cos minus 120 degree, and then we have plus J sine minus 120 degree. Okay, so by doing that, and finally you found out that V line to line, VAB, is actually equals to root 3 V phase and plus 30 degree. So this actually with respect to V phase. So your VAB is a reference voltage. VAN is your reference voltage. Okay, so and that's why this is by mathematical we solve it mathematically. You use a mathematical method to solve, or you can draw. If you have a proper ruler, you can properly, and protector, there is the protector, the one that with the angle, okay? So you can measure exactly the 130 degree there, and then you make sure that you have the same length between that, and find another one there, and you use the we call it the protector to measure the 120 degree, and then you do the VAN minus VBN, and then you measure this VAB, you get the exactly root 3 V phase. Okay, and the angle here, if you measure with the protector, you get the 30 degree. Okay? So uh, that's why we have this root 3 in the front of, whenever you want to change from V phase to V line to line. That's all for Y connected. This is only applicable for Y connected. V line to line is always root 3. The magnitude is always V phase. Okay, so that comes from this equation of by solving this vector VAN minus VBN, you get that root 3. So you need to understand, you need to know why this, how this root 3 appear in the equation here or formula. So that is why, because we use this, we solve this, and that's why you get right root 3 over V phase. This is very similar to whenever you want to get the RMS value, isn't it? RMS of a sinusoidal waveform. This has been, we have looked at last semester doing what we are doing a Powertronic. Okay? VRMS is a root mean square So it's always V peak over square root 2 for the sine wave, isn't it? So why? Because we do the root mean square, which is VRMS. The root mean is 1 over t, 0 to t, v t dt, and then you square the function, isn't it? So by solving this sine function here, finally you will find that VRMS for sinusoidal is always V peak over square root 2. Okay, so as an engineer, Don, you need to know how this you obtain that line-to-line voltage equals to root 3 V phase, and so on and so forth. Okay, so for Y connection, there's no issue on the current because line current will always equals to phase current. Okay, line current will be equals to phase current. However, your line to line voltage, you need to mention V line to line. Do not write only V line. Okay, this is not appropriate. When you write V line to line, that means line A to line B. So that has to be properly addressed. So V line to line is actually from VAB. If you refer to VCA, that's from A and C. VAB, VBC is between B and C. Okay, and that's why you have that. And this is the current IA, IB, IC. Right, so that is the three-phase connection for Y connected. And remember, if you have VA, VB, VC, this is known as, you see this positive sequence, right? If it's a negative sequence, we have VA, VC, VB. But normally, we always use this positive sequence. Okay, positive sequence. Okay, so next, we look into the delta connected system. Okay, this is a delta connected system. So for delta connected system, it's very obvious now. V line to line will be equals to phase voltage, isn't it? V line to line will always equals to phase voltage, and is opposite to the Y connection. Now the current is actually uh, differs. I mean IAB we define. You need to what do you call it, marks properly at the direction of the flow of the current. Okay, so it has to be. So if you look at here, it has to be ICA should be going that way, negative, plus. So it's always out of the positive terminal for the supply, and then this is IBC, and then you have another one, IAB. Okay, so it will flow in that direction, anti-clockwise. Okay, and therefore if you start with the IAB equals to I phase 0, then you write that, then you have this IBC further 120 degree. We have another one which is ICA equals to I phase minus 240. So very similar to uh, the what we call it delta Y connection, but for the delta connection, you look into the note here. You need to use a Kirchhoff current law, whereby you have this IA, what do you call it? IA plus ICA. Why? Because that leave leave the node A, isn't it? Leaving node A, so it's IA plus ICA equals to the current that entering the node, which is IAB. So that's why you have this equation. IA equals to IAB minus ICA. So you solve that, and you find out that your current is root 3 I phase minus 30 degree. Root 3 I phase minus. So this is lagging, which means if you have this is a IA Okay. Uh, so the line current will be equals to IB minus IA. It's a lagging the IAB phase current with a minus and 30 degree. And so you can draw that. That will be your phasor diagram. Right? IAB. This is your IBC, ICA. So very much IAB minus IBC. Oh, sorry. Sorry for that. So you will get that. This is your line current. IA. So the line current goes to root 3 IA. Okay, line current equals to root 3 I phase minus 30 degree. Right. So that is the Y delta connection. And for three-phase power equation, okay, we start with the right in terms of phase quantity. This is known as phase quantity because you address it three times, right? Three times, of course, V phase, I phase, cos theta. Okay, so this is phase quantity. So it's always 3V phase I phase cos theta. And then for reactive power, 3V phase I phase sin theta. And apparent power equals to S 3 times V phase I phase. V phase I phase. And therefore, you can convert that. Oh, sorry for that. For line quantities, if you want to represent in terms of line quantities, this is phase quantities. If you want to put in line quantities, you just simply replace either V phase or I phase depending on the connection. If it's a Y connected, so you change the V phase, isn't it? Because we know that V line to line for Y connected system, V line to line equals to root 3 V phase, and therefore you replace, substitute V phase here with V phase equals to V line to line over square root 3. Okay, and therefore get that. Then I line equals to I phase. That's why you just simply put as IL here, cos theta, and you find out that the output the power for the three-phase power, you get root 3 V line to line, I line cos theta. And that also happens to delta connected. Instead of V line to line, you change the I line equals to 1. The I phase here equals to I line over root 3. Okay, solve that. Okay, so similar equation, same equation, sorry, it's the same question. So either Y or delta connected, you always get the P three phase is always root 3 V line to line, I line. Right? The total power is always root 3 V line to line, I line, cos theta. Okay, clear that? So regardless of the connection, the power equation are the same. However, theta is the angle between phase voltage and phase current. Right. So now we look into the induction machine. Okay. So let's look at the fundamental of induction machines, how the machines work, right? How the machines work, and we look into the component inside the machine, and how to consider and how to start the explanation of how the circuit works. So we're going to look at the rotating magnetic field and some of the fundamentals for the induction machine. Okay, induction machine. Right. So three-phase induction machines are the machines most frequently used in industry compared to the DC machines. Induction machines are commonly used in the industry. Induction machine can operate both as motor and generator, however, seldom used as generator due to the performance characteristics as a generator are not satisfactory for most applications. So, very much IM is used for motor operation compared to generator. Generator usually we use the synchronous machine to be as a generator. And then IM is still used as a motor in many applications. IM has a uniform air gap. So we're going to look at how you get this uniform air gap there. Right, so let's look at the component of the induction machines. So the static component is known as the stator, isn't it? This is a stator, and then this is the one that rotates, and it is known as a rotor, isn't it? Rotor, yeah? Rotor. Okay. Uh, Composed of lamination. So laminate, which means you have a winding, and then you put in slots there, and then you have a three-phase winding. Okay, so each will be connected to phase A, phase B, and phase C. So three-phase winding is put in slots cut on the inner surface of the stator frame. And three-phase stator winding are 120 electrical degree apart and can be connected to the S star or delta. And then if balanced three-phase current flow through the windings, a rotating magnetic field of constant magnitude and speed will be produced in the air gap and will induce current in the rotor circuit to produce torque. So when we start to discuss on the circuit operation, we're going to consider the rotating magnetic field that produced by the stator. This is the starting of the operation, how the induction machines works, right? So we're going to look at later, and now we just proceed. So, and then we have the rotor. Again, it consists of laminates, ferromagnetic material. So both stator and rotor has this ferromagnetic material. So it can produce, when the current flows, that it can produce the magnetic field. Okay, we slot the current space, and there are two types of rotor. There be squirrel cage or wound rotor. For squirrel cage, we're going to see that this is the aluminum bar connected in slanting. Slanting is not straight. It's not straight, but slanting. It's a bit. It's not really straight. So it's a bit slanted here, and we have aluminum bars connected from that end to another end, and you have this aluminum ring to terminate or to connect all of these laminated bars. Okay, all right. So this is known as the rotor, and that rotor will be connected to the shaft and will be connected to the loop at the end here. And there's a fan blade to cool down the rotor. It has an internal fan blades, and then you have a laminated core. And then for wound rotor, very much you have this winding wire here, right? So this winding wire, again, it consists of three phase, and the end of that will be connected to this slip ring here. It will be connected to that, and that will be connected, terminate. And this become the starter circuit and short circuit, and connected to three brushes are short circuited. Okay, right. So that is the comparison between squirrel cage and wound rotor type. Alright, so now we're going to look into the revise, go back how the motor can rotate. Okay, so first we need to consider the rotating magnetic field. So before we start to look into the rotations of the rotor, we start with the rotating magnetic field produced by the stator. So let's say that we have these 6 salient poles. Okay, 6 salient poles, which means A will be having that pair of poles, pair. Okay, so 1, 2, that means we have 2 poles each for each phase. So you have 6 poles, and this is produce the north, and this is south, right, of the phase A, and this is phase B and phase C. So they are physically 120 degree. There is a difference between each phase there. Okay, so when the current flows, okay, when the current flows into your ferromagnetic material here, it produces the the magnetic field, and the magnetic field will produce the direction of the magnetic field produced in your stator here will follow the right hand Fleming right hand rules, is it? It's the right hand rules. So if I zoom this, if I can zoom that, look at the winding, how it wound. So this wire will be wounded to that. Okay. So therefore, if you pass the current through here, so there will be a magnetic field that will be flowing in that direction. Right? So you have that. Your hand, right hand group, so you grab the pole and your thumb will show the magnetic field produced by that pair. Okay, so this is the magnetic field produced in that pair. And then for IB, so current flowing through here. So that means the current actually flowing through that three. That way. So if you grab the B pull, the magnetic field will be in that direction. Three. Okay? Okay, so let's look at how there is a revolving, how the magnetic field produces revolve, it rotates. Okay? So let's consider this sinusoidal current flows. We start with the IA at maximum. Okay, so when you have a IA at maximum, of course, the total or the uh, the highest magnetic field will follow IA, the current IA, isn't it? So IA is at the maximum, so the magnetic field will follow the direction of IA, produce a phase A, so you're going to have that direction of your flux, okay, at position 1. Okay, when you move into position 2, which is that one, okay, now you'll be having IC at maximum, isn't it? So you're going to IC, it's a negative, okay? The negative current IC will be at maximum. So when you look at this current, okay, so instead of if you look carefully, the positive will be that way, isn't it? If you have a positive current, you flow in that direction. Okay? But now you have a negative current. Okay? Again, IA, IP, and IC. So here we're going to have a negative current flowing, which means instead of that magnetic field, your magnetic field will move in the opposite direction. Okay, so we start with that, and now your magnetic field, the what we call it, the total, the highest magnetic field will follow in that direction. We start with that, and for the, we go straight to point 3. Okay, so we have a point 3. Let's look at this point 3. Let's see. Point 3 is when you have a positive IB at maximum. So where is the IB? There you are. Okay? So this is IB. So current flow in that direction, positive IB, and therefore if you grab the pole, you'll see that the maximum, the total magnetic field will follow that direction. So if you look carefully, your magnetic field start with that direction, and then move clockwise, and then move into that clockwise direction, and for the whole cycle from point 1 to point 6, it actually rotates. So one cycle, it rotates clockwise. So that's why we have this rotating magnetic field inside your stator with the three-phase supply voltage applied to the induction machines. Okay, so that is the very first point. I would call it fundamentals, the theory that you need to understand. How you get that rotating magnetic field inside your stator. Okay, so next, when you have that, okay, the speed of the magnetic field, the equation for that is equals to 120 multiplied by F divided by P. Right? So we have 120 F divided by P, so that we give you RPM in terms of RPM of the how the speed of the rotating magnetic field. So if you have a 50 hertz here, and if you have a 6 poles, so very much you have this 120 multiplied by 50 divided by 60, so 120 multiplied by 50, and then you have divided by 60, so you get very much this is to 1000 RPM. Yeah? Revolution per minute. So 1000 RPM. So 1000 revolution, we will rotate 1000 times in 1 minute. Then we get 6 poles and 50 hertz frequency. Okay, right. So how to, now we move into how the rotor rotates. Okay, so how to rotor rotate, we look into the principle of operation. We start with, just now we have the uh, okay, just now we have the rotor, isn't it? So the rotor is going to be, okay, okay, let's quickly draw that. So this is the rotor, and there is a bar connected to in between that. Okay, so this is a rotor. And we have the rotating magnetic field outside there, isn't it? So this is a rotor, and we have rotating magnetic field NS 120 F over P, so it rotates 120 multiplied by F over P. So to look into how the rotor rotates, so we need to cut this off. So we try to cut this off, and then you lie down. You lay down, sorry. You lay down the rotor and it become a ladle here, isn't it? Yeah? So uh, actually, if you can connect that to that point, it become a circle. Yeah? Okay. So now we cut this and then we lay down the rotor and it becomes the ladder here. Hmm? And both sides are connected to a bar, copper bar just now, and it's a short circuit, and that should be a. So how? So this is the rotating field, magnetic field that represent, we put as a permanent magnet here, and it moves in the with the speed of v. Okay, so we must imagine that the permanent magnet here, okay, move to the right with a certain speed of v, and let's look at what happens. Okay, so the first one is that when there is a permanent magnet placed above this conductor ladder, moves rapidly to the right of a speed so that it might, if it sweeps across the conductor. So the following sequence events take place. So the first one, when you start move that the permanent magnet, there will be a voltage induced in each conductor, which means when you start to cut the magnetic field, cut the copper wire here, there will be a voltage induced across that uh, copper there. Okay, so there will be induced there, and that known as a E equals to BLV. BLV. So B is the magnetic field, L is the length, Here length by 2 here, and then you multiply by V, and the speed of the magnetic field, so that gives you E. So this voltage is not actually result by the Faraday law. It's because of the flux, so by using the Faraday law, there will be a voltage via V induced for each conductor when it's being cut by the flux. Okay, next, since the conductor is short-circuited, there will be a current immediately flows in the conductor winding, in the rotor winding. So, come back here, there will be a voltage induced, and there, because it's a short circuit, and therefore there will be a current flow here, right? And the current flows through that as well. Okay, and this current, the current carrying conductor lies in the magnetic field. So this conductor lies in the magnetic field, rotating magnetic field. So that experiences a mechanical force. Because of that, because of the Lorentz force, the conductor here, okay, will experience some force due to the Lorentz force, and it will be dragged. It will drag following the direction of the motor, the magnetic field. So the force will follow the direction of the magnetic field. So it will drag the ladder here to follow the magnetic field in that direction. Okay, so that is known as a Lorentz force. The force always acts in the direction to drag the conductor along with the magnetic field, and this is a Lenz law. Something about Lenz law and Lorentz force, and that's why you have the rotor now will rotate in that direction. Okay, so is it going to rotate with the same speed of the rotating magnetic field? The answer is no. Okay, the rotor here will always rotate with the speed, or will drag to the right hand side slightly. The speed will be slightly lower than the ns, the synchronous speed. This is known as the synchronous speed, and the rotor is n. The rotor speed is n. So there is always n lower than ns. Okay, so why, you can imagine, as we have this we call it, this is rotor disc, right? So we have a hand drill. Well, we have a hand drill here, and both are connected to a stator disc and rotor disc, and there is a rough surface in between them. Okay, so when you rotate, or when you start to rotate the handle of your stator disc here, there will be a slip. Right? The rotor disc here will always not going to catch up with the stator disc. There's always a slip between rotor disc and stator disc, isn't it? Right? And that is so that's why we have n always lower than ns, slightly lower than ns. We not follow exactly as ns, but slightly. This is why we have the slip terms come into your terms here. The slipping clutch, right? Two disc with approximate torque transfer through rotor disc, slipping against the disc. So effort to turn the stator disc come from the mechanical torque, and there is a friction loss as well as the rotational energy of disc. So the RPM, how fast is the slip? You can simply minus and s minus n, that gives you the slip RPM. In terms of revolution per minute, so you can measure that. The speed is always ns minus n. And so that is known as the slip. N is the speed of the rotor, and ns is the speed of the rotating magnetic field. Hmm? So just imagine this clutch, the slipping clutch, for example, to this here with the handle, then you can imagine how you get that S. Okay, So the definition of slip, you can, this is, I think most of you have still remember this. S is known as the slip, and S minus N over and S. And then there is a frequency of F2 induced in voltage and current in the rotor is defined. So remember, when there is permanent magnet that move above the conductor, and there is a voltage induced across the rotor, isn't it? And that the frequency of the voltage and current induced in the rotor will be equals to F2. Okay? So F2, and the what we call it, uh, the frequency is given by this 100. We know the N S equals to 120 F over P, isn't it? So for the slip, become F2 here, P multiplied by N, this will be replaced by NS minus N, divided by 130, multiplied by P, so that gives you the slip frequency, that given by the F2 equals to SF1. P F2 equals to SF1. So the frequency F2 is always very, very small compared to F1, because S normally is very small numbers. It's 0.1, 0.2, 0.01. It's very small slip uh, between rotor and the magnetic field. So the equation is F2 equals to SF1. It's a friction of the frequency for your stator. And then now we look into the induced voltage. So the induced voltage will be for in this equation. Okay, this actually come from uh, E equals to the negative D flux over dt, flux linkage over dt. Okay, and from this equation, that's why you have the 4.4 over uh, extinction. Okay, the RMS. This is known as the RMS value. You can refer back to how you get that. And this is RMS, a voltage across your circuit, rotor circuit. So you become 4.44 F2. N2 is the winding turn ratio. Flux P is the flux produced by the primary. Uh, and then we have the constant Kw2. This is known as a constant. And therefore, if you substitute the F2 with SF1, you get this E2S equals to SE2. So E2 is the standstill voltage. And standstill voltage. So if we look further, E2, the standstill voltage, which is the voltage induced in the rotor while the rotor is at standstill. It doesn't move yet. Okay? At standstill, which means rotor doesn't move yet. Okay, and that's why you have E2, and there's a frequency of F1, because the rotor doesn't rotate yet. There is no the rotating magnetic field. There's no rotating field yet. Okay, and this is known as standstill operation. So E2 operate at F1. So that's why you have this E2, known as induced voltage at standstill. So the motor doesn't rotate yet. Okay, and so the induced current in the three-phase rotor one is also produced. A rotating field rotates at speed of N2. So the induced current in the three-phase rotor, remember, the current also induced in the rotor. So that current also produce a rotating magnetic field. Okay, not only the stator that produces a rotating field, the rotor also produce the rotating magnetic field, and the speed is N2. Okay, the speed is N2. The rotating speed of the is N2. So N2 equals to 120 F2 over P. So if you replace with F1, you get the S and S. uh, S, S, S. So this is F1 here. Uh, let's put S F1. So it is the friction of the synchronous speed. uh, The rotor also, the rotor rotate with the speed of N. Remember, the rotor rotate with the speed of N. Okay, why it rotates with the speed of N? There is a rotating magnetic field that also rotate with the fraction of S and S. Okay, so if you look carefully, the rotor itself is rotating at the induced rotor magnetic field. So if you look outside of the rotor and the motor, you put yourself outside of the rotor and stator, you will see that this rotating magnetic field that produced by the rotor also rotate with the same speed of ns by the stator, isn't it? So now there are two components of magnetic field in the air gap. One is due to the stator and the other one is due to the rotor. Okay, the rotor, and both have the same speed. So therefore, the last sentence here said that therefore both magnetic fields that can rotor rotate at the same synchronous speed. The interaction between these two fields can be considered to produce a torque. So the interaction between these two magnetic fields that produce the torque, which drag the rotor to rotate. Eh? To rotate. Okay. Uh, so let's look back at the standstill operation. So for standstill operation, remember E1, the voltage in the stator side, 4.44. This comes from the RMS voltage. You can look back at some books how you get that. So very much you come from E equals to D flux linkage here divided by dt. So you integrate so that. You can refer to PC set book if you like. Okay, PC set book, or you can find out how you get that 4.44 F1 and 1. Okay, and for E2, okay, the standstill, remember the standstill, nothing happened yet. So the voltage across your rotor will have this 4.44 speed, frequency F1, and 2 flux plane. So this is known as reduction factor due to this one. So very much similar, K omega 1 equals to K omega 2, and you can cancel that and you get this equation E1 over E2 equals to N1 over 2. So that is the standstill. And you can also look into the running operation. Once you understand the circuit, I mean the backstage, how the rotating magnetic field inside the air gap, you will answer this question. Okay, you can get it. So you can refer to PC Sense book, page 219. This is a very good book for induction machines. Let's tell you, this is a very good book for the induction machines. Right? It's a PC Sense book. PC Sense. Okay. Also, you can find it. Okay. I'm going to share this example. There's a question. There's this answer solution for that. So the question is very testing your understanding on the circuit operation. Determine synchronous speed, speed of the rotating air gap, frequency of the rotor circuit, slip RPM. So once you understand the operation, then you'll be able to uh, to answer these questions, right? Speed of the rotor field relative to the rotor structure, relative to the static structure, as well as the static rotating. Okay, now let's look into the three modes of operation. So to be able to get these three modes of operation, So we can imagine that your induction machines here will be coupled, will be connected to a DC machine here, and the shaft is connected to the DC machine. Why? Because we want to rotate at, to get into the modes here, three modes of operation. This DC motor will help to rotate the rotor here. Okay, so that you get into the. Okay, first we look into the motoring state. And this is known as a torque speed characteristic unit for induction machine. Okay? So for induction machines, we have torque again speed, torque again speed. Okay, so here if we look closely, n equals to 0. Great. So for motor, for AC motor, induction motor, we don't say as a holding state, isn't it? For DC drive, you know, there's when n equals to 0, that is referred to the holding state. Okay? But for now, for the induction machines, the torque that produced at that point is known as the starting torque. Okay, T start. T start. Why? Because n equals to 0 at that point. Okay, n equals to 0. And then you have this T what? Maximum torque. Okay. This is the maximum torque. And the speed at that is known as the n speed, and T max, the speed at maximum torque. And you can also calculate for S T max, the slip at maximum torque. Okay, so you can calculate that. And then we have this torque equals to 0. So here, when you have n equals to ns, right? When n equals to ns, so there is no torque produced. Right? Okay. So here, this is known as the motoring mode. When you have a negative speed, this is where your rotor rotates in the opposite direction. That is known as the plugging or braking modes of operation. And finally, when you have a torque which is the reverse, you can get a generating mode. Okay, and this is where you have S equals to at that point. Okay, at that point, S equals to what? S equals to 1, isn't it? S equals to 1. And that point, S equals to 0. Since n equals to ns. Okay, so that one. So beyond that, then we get a generative. Okay, so in motoring, ns is always greater than n. And in generating mode, you're going to get the speed of the rotor rotate higher than the synchronous speed. Okay, synchronous speed. So you can read that. So how to do that? It is achieved by rotate the rotor by using that DC motor. You're going to rotate that, and then it will uh, be in the generating mode operation. Okay, next we have a plugging. So in the plugging state, n is in the opposite direction of your ns. The opposite direction. So that shows the s greater than 1. You have n equals to 0. Okay. Okay. Now we look into the equivalent circuit model. Right. So why we need it? Because we're going to look into the equation, torque equation later on. So in order to get torque equation, we need to look into the single phase equivalent circuit. Okay. And then going to get the parameter. And in in order to get that single phase equivalent circuit, we need to consider the stator and rotor winding circuit here. So for stator, this is very much similar to transformer, isn't it? Transformer, so that's an air gap there. So we in transformer we always somehow we refer rotor circuit to the stator circuit, isn't it? Rotor refer to the primary, secondary to primary. When the rotor, when this, all elements are at the all parameters, all components in the refer to the primary side, the primary side of the transformer, then we do the calculation. So very similar to here, you have an air gap, and this is the stator winding. Okay, so you have R1, X1, RC is a core resistance, as well as the XM is known as the magnetizing inductance. Magnetizing inductance, R1 is 1, and this is the focusing. And then for the stator winding, there's no difference from that. For example, this is higher, so leakage current is larger in IM. Yeah? So mentioned here, IM is as a high 30% to 50% of the rated current, whereas transformer is only 1% to 5% of the current. This to the air gap. Okay, so for rotor circuit, we know that as ET, the rotor that the voltage across your rotor as E2, and then we have this SX2. So how to get the SX2? So let's consider this uh, equation first. So when we are at that F2 frequency, so this is rotor side, isn't it? So the frequency is F2, and therefore the reactance will be 2 pi F2 L2. Okay, so in order for you to bring this to the primary side, you need to change that equation into F1. And instead of F2, you replace that with F1, so it becomes 2 pi F1 L2, and therefore you have S2 pi F1 L2. So the frequency now follows the stator frequency F1. So we do that as X2. Okay, as X2. So the circuit here works at F2 frequency, and when you manipulate the circuit, right, so you have I2 equals to SE2 over R2 plus JSX2. So if you want to, what we call it, we rearrange. We try to rearrange, and we remove S in front of E2 and S2. This is what we obtain. E2 divided by L2. So in terms of equation, there is not much difference in it, but it's actually this circuit, if you redraw it, that circuit actually now working with the F1 frequency. E2, X2, R2 over S, so that work with the F1. Remember, X2 is that one, so 2 pi F1 L2. Then become X2. So now everything works at the frequency F1, and that's why you have the term R2 over S. Okay, so from there, note the per phase restricted power. So there's a air gap power. P equals to I2 R2 over S. So this is the power at the rotor side. Since slip S is usually low, so the power P is considered large. Isn't it? Because S is very low, therefore P is considerably very large. And the R prime 2 there components can be separated, can be represent, you can separate that R prime 2 over S into this equation, into this component R2 and R prime R2 over S 1 minus S. So that produce the heat. Just simply a R2 there will produce a heat, and that actually produce the mechanical power developed. P max R prime 2 over S 1 minus S. So if we add these two become R2 again, R2 over S. But in terms of the power, there is a different power that actually produces a drop of, we call it a loss, okay? And this is the actual power within the developed mechanical power developed. So Pmax equals to I2 over R2S. So I multiplied by that will give you I squared multiplied by that will give you Pmax. And then you can manipulate or calculate get Pmax is 1 S over P2. Therefore, P2 equals to SPAG, the air gap. Okay. P2 is the power, air gap power. This is the power in the rotor side. So you can have this ratio. Okay. So that you can simply do the PAG divided by P2 equals to what? 1 over S. So if you take only that, you got PAG divided by P2 equals to 1 over S. Therefore, P2 equals to S multiplied by PAG. Okay. And if you want to equate that in that, you can take that like that. So it becomes P2 divided by Pmax equals to S divided by 1 S. Okay. So Pmax equals to S multiplied P2 1 minus S over S. Okay. Okay. The total power input to the rotor is known as a P air gap, PAG. Total power input to the rotor. A fraction of S is dissipated in resistance. A fraction of 1 minus is converted to mechanical power. And should operate low frequency slip to increase the efficiency. Part of Pmax loss to friction remainder will be available as the operation power. Okay, so the complete circuit is going to be that. This is the stator side, and this is the secondary side. So when you want to solve and to look to get the parameters, important parameters, we have to bring this into the primary side. Uh, from the rotor side, you have to bring to the stator side, and that's why you have this. If you look carefully, it's a X prime to R prime to this means that you refer all the parameters from the second to the primary side. So you get that, and you can look into the example 5.2. I'll get all the values there. Okay, I leave it to you, and then we look at the various recovery circuit operation. So for approximate circuit, remember, I hope you still remember, you can bring the branch here, RC and XM, to the front end, isn't it? If you use the approximate equivalent circuit. And because R can be rotation loss, so, and we know the XM is very large compared to RC, so you can simply remove that. So you got this one, and here we have XM. Okay, consider small voltage drop and equal sorry, simplify computation. RC can be removed considering that at no load is small, so RC can be removed. So the justification to remove that is listed here. Okay, try to understand. So that means you can simply remove RC. And for IEEE recommended circuit that you maintain all components in its position. Only RC can be removed. So we actually actual circuit, yeah, still have RC here. But because of that statement here, what is it? Where is it? We can remove RC somewhere. Okay, this is also statement that shows that you can remove RC. Okay. Okay, what? So, okay. So X1 is also large because of the air gap, right? Since it's touching current is 30% operating current, and so you can remove RC. RC can be measured with the same resistance as mentioned in the circuit. Right. So RC can be removed, and what you see is only that. So you have R1, X1, XM, X prime 2, I prime 2. Okay. So for I2P recommended, it is advised that you convert that into different voltage rate. VTH, ZTH, you need to get that component. And how to get that? You make sure that you look from that angle. Okay, and you look to the angle, and you need to get the VTH as well as the ZTH. So in order to get the VTH, you need to short circuit the voltage, and then look from here to the left hand side. So you're going to see that XM is in parallel with R1 X1. So that gives you RZTH, and basically if you want to get the VTH is the voltage drop across that, so you can use the what do you call it, voltage divider rule. You apply the voltage divider rule, so you'll be able to get that voltage across your uh, terminal here, and that is your VTH, and you become that. So VTH, so it's here, and then multiplied by V1. You apply voltage divider rule, and you can also look at ZTH. Okay? ZTH. Okay. Good. So you stop for that, and you got that. And that this is a no load test, block the test, this is a revision. Okay. And finally, the performance characteristic, you can understand that. Okay. Right. So Tmax, the mechanical torque per phase. Tmax equals to torque max. So you know that, um, and also equals to that. You know this equation, isn't it? Tmax omega max equals to I2 R2 over S minus S. And then omega mechanical equals to 1 minus S, which is the rotor side. 1 minus S is N. Which is N equals to 1 minus NS. 3. This is the omega radian per second. So you solve that, This is the key equation that we're going to use for your DC AC drive. This equation. Okay, so we need to get what is a VTH, then RTH. Okay. So this is Tmax, P air gap over omega C. So this is only one phase. This is Tmax for one phase. Tmax for one phase. And so for three phase, you just simply multiply by 3. No worries. You simply multiply by 3. And this is, you can read further how you can approximate Tmax equals to 1 over omega x VTH squared over R2S. This is R2. Okay, this is again approximation. And we get that. This is how you get that estimate. So to get the maximum point here, what you can do is you differentiate once. Differentiate once here. D top over ds, and you set that equals to 0. So you get the maximum point, isn't it? And this is the mathematics. So if you have 1 point, if you want to get the maximum point here, so the slope should be 0. And the slope here should be 0, isn't it? So if you, at that point, if you differentiate, you get that. Right? And this is always the slope. So therefore you set that to 0, and that gives you as Tmax. You also get the Tmax equation. And this is the Tmax equation. For three phase, you just simply multiply by 3 here. Okay. The maximum top. And then extend still. Okay. Set as equal 1, you get the equation here. And this is the power flow. Power flow. So starting from the input power and the stator side, isn't it? This is stator side. We have stator copper loss, stator core loss, stator copper loss. That will produce you air gap power. And the power inside your air gap is a PAG. Then if you minus with the rotor loss and the copper loss, that gives you the mechanical developed mechanical torque. And then if you minus with the friction, that will give you the final output shaft power. Okay? So, thank you very much. You can try this example. Okay, so I hope you get a bit on the circuit operation. Again, try to find this PC Sense book to understand all the. I mean, it's a good explanation on the circuit operation of the next machine. Okay, so next week we can next is we go to look further into the AC drive. Now, once you understand this induction machine, the S, what is the sleep, and the mechanical torque equation, and then the power flow, and then from that, we're going to look into how we can control the speed and so that it rotates with a certain speed that we require. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.